Welcome to the third video in our Class 7 series of lecture videos for our notes. You will need to be able to draw chair cyclohexane with equatorial and axial substituents. Of course, it's always nice to practice. So let's consider the conformers of methyl cyclohexane. We could have a chair conformer in which our methyl group is axial. And of course, if we flipped that chair to the other potential chair conformation, the methyl group would be equatorial in that other chair conformation. So which conformation is energetically more stable? And then we need to ask the question, why? And so table 4.3 in your assigned textbook and the syllabus gives thermodynamic parameters for various cyclohexane substituents in a certain conformation, be it axial or equatorial, on a various cyclohexane chair conformer. So I hope we remember from general chemistry that the change in Gibbs free energy is equal to negative R times temperature times the natural log of our equilibrium constant. R is 8.31451 joules per mole Kelvin. They're 4.184 joules and 1 calorie. Temperature is, of course, represented as T, and it's typically given in Kelvin. And for a process where you have A in equilibrium with B, the equilibrium constant KEQ could be defined as the equilibrium concentration of B divided by the equilibrium concentration of A. And I hope we all remember that if your change in Gibbs free energy is less than 0, that describes a spontaneous process. So if delta G is less than 0 for A going to B, then A will spontaneously convert to B. If delta G is greater than 0, that describes a non-spontaneous process. All right, so the table gives various indications for the change in free energy, delta G, on going from a cyclohexane chair conformer with an indicated substituent axial to the cyclohexane chair conformation with the indicated substituent equatorial. Here we have that set up for a cyclohexane chair conformer where we've got an R group in the axial position going to the conformer where the R group is in the equatorial position. For R equals methyl CH3, also abbreviated as Me occasionally, the change in free energy on going from that conformer where the methyl group is axial to the conformer in which it's equatorial is negative 1.7 kcals per mole. And of course, the associated KEQ with that is about 17.8. So what this is telling us is methyl cyclohexane prefers to be in the cyclohexane chair conformation where the methyl group is equatorial and not axial. And we'll see why in just a moment. For the R group of ethyl, it's not too much different at negative 1.75. Changing one of those hydrogens on that methyl group to another methyl group doesn't severely increase the spontaneity of that conversion. However, if you're isopropyl, now you go from negative 1.7 to negative 2.70. So something happened. We got much bigger in terms of our steric interactions with perhaps other areas in that cyclohexane ring. And we really prefer to have that big, bulky isopropyl group in the equatorial position. You can see for the tert-butyl group, we're at negative 5 or greater. It's very difficult to tell. That large groups like the tert-butyl group lock your cyclohexane ring into a chair conformation where that group is equatorial. So for R equals methyl, you could calculate that you have about 95% equatorial methyl cyclohexane chair conformers at equilibrium and about 5% axial. There's still interconversion between your chair conformers, but at equilibrium, 95% of them will be equatorial at a given time. Okay, so we have to ask why. Why negative 1.7? And there's some interesting reasons for that. And something we can relate to now that we've seen gauche butane. So I don't know if you remember, but gauche butane compared to anti-butane was about 0.9 kcals per mole higher in energy. So we can see quite clearly if we do a Newman projection on this methyl cyclohexane conformer in which our methyl group is axial, coming off carbon 1, that methyl group is gauche to what? Carbon 3. So there's a gauche interaction. That's one gauche interaction between the methyl group and carbon 3. Now if we turn the conformer around and instead of sighting down the 1,2 carbon bond, now we're sighting down the 1,6 carbon bond, we see, oh, wow, there's a gauche interaction between the methyl group and carbon number 5. So 2 times 0.9 kcals per mole for each gauche butane-like interaction in organic chemistry math is 1.7 kcals per mole difference. So this is why our cyclohexane conformer with the methyl group axial is 1.7 kcals per mole higher in energy than the cyclohexane conformer with that methyl group in an equatorial position, because we possess 2 gauche interactions between that methyl group and other carbons in the cyclohexane ring, specifically carbons 3 and 5 as we labeled them. So to be thorough and complete, an organic chemist would, of course, draw a Newman projection for the cyclohexane conformer where the methyl group is equatorial. And so if we do that, you can see now that this methyl group is staggered between hydrogens and it no longer possesses any gauche interactions inside the ring. So no additional gauche interactions with the methyl group and carbons in the ring. One should also observe the 1,3 diaxial interactions, also called transannular interactions, between the methyl group and the axial hydrogens. In fact, these are exactly the gauche interactions between the methyl group and carbon 3 and the methyl group and carbon 5. It's not that the methyl group is bumping into carbons 3 and 5. It's actually bumping into the axial hydrogens that are coming off of carbons 3 and 5. So that really is your gauche butane interaction. It's between the hydrogens on the methyl group and these axial hydrogens on carbons 3 and 5 in the ring. And of course, when that ring flips to the conformation where that methyl group is no longer axial but rather equatorial, there are no longer any methyl hydrogen 1,3 diaxial interactions, or those gauche interactions that I observed. And just to show you that this isn't just all on paper, that it's actually a physical reality, here's methyl cyclohexane chair conformer. I hope everyone can see that the methyl group is axial. If we sight down this carbon-carbon bond, this carbon-carbon bond, what do we see? We see this methyl group is gauche to this carbon, right? Which really means it's the hydrogens on the methyl group that are bumping into the axial hydrogen on this carbon. And then if it's gauche to this carbon, it's also gauche to that carbon over there, but we would need to turn the molecule around and sight down that carbon-carbon bond to see, oh yes, this methyl group is gauche to this other carbon, which really is the 1,3 diaxial interaction between the methyl's hydrogens and this axial hydrogen. And like I said, to be thorough and complete, we should flip this into the other chair conformation, which the methyl group is equatorial, and now we no longer see any gauche interactions between this methyl group and other carbons in the cyclohexane ring. So this is the low energy conformer by 1.7 kcals per mole, and we discovered that the reason for that is two gauche butane-like interactions, each of which is worth 0.9 kcals per mole. That 0.9 value is probably 0.85. They just rounded it up to a significant figure of 0.9, and 2 times 0.9 is really 2 times 0.85 to get the 1.7. So that completes this video. We'll see you for the next one.